Have you ever seen a wheel in a movie spinning backwards while the car is clearly moving forward? Or drops of water dancing on a hot pan like they're alive? A ping-pong ball just hovering in midair above a hairdryer? A magnet literally floating above a track like some sci-fi train? Or a bike that somehow stays up much better when it's moving than when it's standing still? All of that feels like CGI or magic tricks, right? But nope, it's all physics. 100% real, 100% explainable. In the next few minutes, I'm going to walk you through 5 physics phenomena that look exactly like magic tricks, but are actually just the rules running quietly underneath our everyday lives. If you stick to the end, I promise, every time you see a spinning wheel, a plane taking off, or you hear that breakfast bacon sizzling on the pan in the US or Canada, you'll remember this video. Alright, let's dive in. Phenomenon number 1, the wheel that spins backwards on camera. You've definitely seen this one. In Western movies, music videos, or dashcam footage on the highway, a wagon wheel or a car wheel sometimes looks like it's turning backwards even though the car is clearly moving forward. It looks like bad CGI or some glitch in the Matrix, but what you're really seeing is a classic illusion called the wagon wheel effect. Here's the basic idea. Your eyes and cameras don't see the world as one perfectly smooth, continuous flow. A camera records video by taking a series of still images called frames per second, 24, 30, 60 FPS. If the wheel is spinning just at the right speed relative to that frame rate, your brain reconstructs the motion in the wrong direction. Imagine it like this. The camera snaps a frame. By the time it snaps the next frame, a spoke on the wheel has turned 350 degrees. A full circle is 360 degrees. So that spoke has almost made a full turn, but it's 10 degrees short. When your brain looks at the frames, it doesn't think, oh, this spoke moved plus 350 degrees forward. It thinks, this looks like it moved minus 10 degrees backward. Frame after frame, your brain sees slightly backward, slightly backward, slightly backward. So the wheel appears to spin in reverse. This doesn't just happen with wheels. You see the same effect with airplane propellers, ceiling fans, helicopter blades. If the spin speed and the camera frame rate line up in just the wrong way, you'll see them stand still or even spin backwards. In real life, the wheel is spinning perfectly forward, smoothly. The weirdness only shows up once you slice time into discrete frames and let your brain guess what happened in between. The takeaway is simple. The physical world is behaving normally, but our sensors, our eyes and our cameras have limits, and those limits create illusions. Next time you see a wheel glitching in a TikTok, a movie, or in dashcam footage anywhere in the US or Canada, you can flex a little and say to yourself, not CGI, just the frame rate clashing with the rotation speed. Phenomenon number 2, why a moving bike stays up. Here's a fun observation. If you give a bike a little push and let it roll forward with no rider, no one holding it, it'll keep going for a while before it falls. But if you try to balance the same bike standing still with no movement, it'll tip over almost instantly. What's the difference between rolling and standing? A big part of the answer is something called angular momentum and the gyroscope effect. Think of each spinning wheel on the bike as a giant gyroscope. When the wheel spins fast, it stores rotational momentum. A spinning object hates having its axis suddenly changed. When you try to tilt it, it pushes back in a strange sideways way instead of just falling over. That pushback is what helps keep the bike upright. You can feel this very clearly with a simple experiment. Take a bike wheel off the bike. Hold it by its axle in both hands. Have someone spin it fast, then try to twist it or tilt it. You'll feel this weird, invisible force resisting your motion. That's gyroscopic precession, the fancy term for how spinning objects redirect forces in a way that looks almost magical. Back to the bike, When the bike is moving, the wheels are spinning. The faster they spin, the stronger the gyroscope effect. Small wobbles and tilts get corrected more easily. You still steer and make adjustments, but the physics is helping you. When the bike is standing still, the wheels aren't spinning, there's no significant angular momentum, no gyroscope to fight gravity. Any tiny lean quickly becomes a full fall. This same idea shows up everywhere. In airplanes, ships, submarines. Gyroscopes help with navigation and stability. Inside your phone and inside drones, tiny sensors track orientation. Even a simple fidget spinner is a mini demonstration of the same physics. So when you see a 5-year-old kid in Toronto or Texas riding a bike and somehow staying upright after just a few tries, it's not only natural talent. Physics is carrying them. Phenomenon number 3, the ping-pong ball that floats in air. Picture this. You turn on a hairdryer, pointing it straight up. You drop a ping-pong ball into the stream of air, and it just floats there. It wiggles and shakes, but doesn't fall or fly away. It looks exactly like a magic trick, but it's actually a beautiful demonstration of air pressure and the Bernoulli principle. Here's the short version of Bernoulli. When a fluid, like air, moves faster, its pressure drops. When it moves slower, its pressure is higher. In our hairdryer setup, the air in the middle, where the ball sits, is shooting upward very fast. That's a low-pressure zone. The air around the ball is calmer, so that's a higher pressure zone. The higher pressure from the sides keeps the ball back into the fast-moving central stream whenever it drifts out. At the same time, the upward force from the airflow roughly balances the weight of the ball. The result? The ping-pong ball hovers in mid-air. This same idea is deeply connected to how airplanes fly. Airplane wings are shaped so the air going over the top has to move faster than the air moving under the bottom. Faster air on top means lower pressure. Slower air below means higher pressure. That pressure difference creates lift, which pushes the plane upward. So every time you fly from the US to Canada and look out the window, seeing the wings flexing and vibrating slightly, you're watching Bernoulli, air pressure, and serious fluid mechanics working hard to keep you in the sky. You can try a low-budget version of this at home. Take a sheet of paper, hold it under your chin, letting most of it hang down loosely. Blow air across the top of the sheet. Instead of being pushed down, the paper actually lifts up. Once again, faster air on top, lower pressure, and the higher pressure beneath pushes it up. No invisible strings, just physics messing with your intuition. Phenomenon number 4, water drops dancing on a hot pan. Let's move into the kitchen. You're making breakfast. Maybe eggs and bacon in New York or Vancouver. You heat up a pan and sprinkle a few drops of water to test the temperature. If the pan is just warm, the water spreads out, sizzles, and quickly evaporates. But if the pan is extremely hot, the drops don't spread. They bead up into little round droplets, and then they start skating and dancing around the pan like tiny living creatures. This is called the Leidenfrost effect. What's going on? When the surface is much hotter than the boiling point of water, the water touching the surface vaporizes almost instantly. That creates a thin layer of water vapor between the droplet and the pan. This vapor layer acts like a tiny air cushion, keeping the droplet from touching the hot surface directly. Because there's less direct contact, the droplet actually takes longer to fully evaporate, even though the pan is super hot. While it's floating on this vapor cushion, it can slide and bounce around, giving that dancing drop effect. You'll see similar behavior in industrial kitchens with super hot metal surfaces, and in science demos with liquid nitrogen. Sometimes people dip their wet hand very briefly into liquid nitrogen and don't get instantly frostbitten because of this temporary vapor layer. But here's an important disclaimer. This is not a safety shield you should rely on in real life. Hot oil and water are a completely different story. Water turns to steam explosively and throws hot oil everywhere, so don't play Leidenfrost magician with a deep fryer. The main point is, the Leidenfrost effect looks like some weird anti-burn power-up, but it's really just water trying to escape a surface that's way too hot, leaving behind a cushion of vapor. It's gorgeous in slow motion and deadly serious in a real kitchen. Phenomenon number 5. Floating magnets and quantum locking. Now for something that looks straight out of science fiction. You might have seen this in a science museum or on YouTube. A small disk of material, super cold and smoking with vapor, a track made of strong magnets. Someone gently places the cold disk above the track and it just floats there. They push it and it glides along, still completely levitating.
Sometimes they even flip the track upside down, and the disc still hangs there, locked in midair. This is magnetic levitation using superconductors, and a phenomenon often called quantum locking. Let's unpack it in a simple way. First, what's a superconductor? Some materials, when cooled to very low temperatures, suddenly lose almost all electrical resistance. That means electric current can flow through them without losing energy as heat. In this state, they also develop strange and powerful interactions with magnetic fields. A magnet creates a surrounding field you can think of as invisible curved lines, called magnetic flux lines. Normally, those lines pass through space and materials in a predictable way. A superconductor doesn't easily allow magnetic fields to pass through its interior. It can expel the magnetic field or force it into particular channels. The interaction between the magnetic field and the superconductor creates forces strong enough to lift and hold the superconductor in the air. In some setups, the superconductor isn't just floating. It's locked into a specific position relative to the magnetic field. You can slide it along the track, tilt it, or flip it, and it stays at a fixed distance above the magnets. This locked position is what makes it look like the object is frozen in space. This is more than a party trick. The same basic principles are behind ideas like maglev trains, trains that float above tracks using magnets, reducing friction and allowing very high speeds. Right now, most superconductors need to be extremely cold to work, which is expensive and impractical for everyday use. But scientists are constantly hunting for materials that can superconduct at higher temperatures. If we ever fully crack that problem, you can imagine ultra-efficient power lines, super-fast trains, and new kinds of motors and devices we haven't even thought of yet. For now, floating magnets give us one of the most satisfying physics demos on Earth. No wires, no strings, no visible support, just quantum physics flexing on gravity. Let's recap the 5 magic tricks from today. Number 1, the wheel spinning backwards on camera. Not a glitch in reality, just the frame rate of the camera clashing with the rotation speed of the wheel. Number 2, the self-stabilizing bike. Spinning wheels act like gyroscopes, making it easier to stay upright when you're moving. Number 3, the hovering ping-pong ball. Differences in airspeed and pressure, explained by Bernoulli's principle. Number 4, water dancing on a hot pan. The Leidenfrost effect, where vapor cushion keeps droplets from touching the surface. Number 5, floating magnets. Superconductors and quantum locking pinning objects into midair. What do they all have in common? None of them are actual magic. They all come from simple rules applied in ways that our intuition doesn't immediately understand. Physics isn't just about equations on a homework sheet. It's the backstage toolkit the universe uses to run all the special effects around us. Every day, on the roads in the US, in kitchens across Canada, in planes, trains, and in the videos you scroll past, these magic tricks are happening quietly in the background. If you enjoyed this breakdown, imagine what's next. Natural phenomena that look like CGI but are 100% real. Or optical illusions that prove your brain is lying to you all the time. There's a ridiculous number of tricks left in this universe. We've just started.